Okay, welcome to our discussion of Rubinstein's infinite horizon alternating offer bargaining game. So last time we discussed two examples of finite horizon bargaining, and I just want to begin by recapping what we discovered about the subgame perfect Nash equilibrium payoffs in those games. So what we saw was with one round, so player one makes an offer and then player two either accepts or rejects. The subgame perfect Nash equilibrium payoffs are that player one gets all of the stuff and player two gets none of the stuff. With two rounds, we saw that player one gets a little bit less. If player two rejects player one's initial offer instead of the game ending, player two gets to make a counter offer. And then player one either accepts or rejects. If player one accepts, the pie is divided. If player one rejects, then the game ends and both players receive nothing. And we saw that here, the subgame perfect Nash equilibrium payoffs were 1 minus delta to player one and delta to player two. Remember, this delta is a discount factor. It's a number greater than 0, less than 1. It measures the value of time. It measures the rate at which the prize to be divided, becomes less valuable. And we see here that giving player two a round to make a counteroffer gives player two a little bit of power relative to player one. So we won't derive the subgame perfect Nash equilibrium strategies in 3 or 4 or more rounds, but I do want to tell you what the subgame perfect Nash equilibrium payoffs are, and we're going to use this pattern to develop an intuition for what we think should happen in the infinite horizon alternating offer bargaining game, and then we'll derive that subgame perfect Nash equilibrium with infinitely many rounds. So if we added a third round, player one's payoff in subgame perfect Nash equilibrium would be 1 minus delta plus delta squared, and player two's payoff would be delta minus delta squared. And then in round 4, with 4 rounds rather, we should say, player one would receive 1 minus delta plus delta squared minus delta cubed. Player two would receive delta minus delta squared plus delta cubed. And the pattern would continue if we added a 5th, 6th, or however many rounds. So what we see is every time we add a round in which a player gets to propose, her payoff in subgame perfect Nash equilibrium goes up a little bit, and the other player's payoff goes down. So here in round 1, with one round, player one gets all of the pie and player two gets none. But with 2 rounds, so the second round would be the round in which player two gets to make an offer, gives player two a little bit of positive payoff in subgame perfect Nash equilibrium, and player one loses out a little bit. If we extend to 3 rounds, in the third round, player one would get to propose a division between the two players. That gives player one a little bit more leverage, so her payoff goes up a little bit relative to how much she would have received in a 2-round game, and player two's payoff goes down a little bit relative to what player two would have received in a 2-round game. And then similarly in 4 rounds, the 4th round is a round in which player two gets to propose, so player two's subgame perfect Nash equilibrium payoff goes up a little bit, while player one's goes down. So we want to ask ourselves, what happens as the number of rounds goes to infinity? We have 1, 2, 3, 4, and we should ask ourselves what happens if we keep this pattern going. This isn't a derivation of the payoffs in subgame perfect Nash equilibrium. It's certainly not a derivation of subgame perfect Nash equilibrium strategies. This is just to provide a little bit of intuition for ourselves so that when we derive the actual subgame perfect Nash equilibrium and its payoffs, we'll see that it matches up with our intuition, and that will help reassure us that we did it right. Okay, so what happens to this? Let's first think about player one's SPNE payoff. it should be 1 minus delta plus delta squared minus delta cubed plus delta to the 4th minus delta to the 5th plus delta to the 6th minus et cetera, et cetera, et cetera. So if we want to get rid of this dot, 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 and write this somewhat more compactly, this is equal to the sum from t is equal to 0 to infinity of minus delta to the t. So let's check. If t is equal to 0, minus delta to the 0 is 1. When t is equal to 1, minus delta to the 1 gives us minus delta. When t is equal to 2, minus delta to the 2 is equal to plus delta squared, and so on and so forth. So this form, where we can look at this somewhat less formal expression, shows us that in subgame perfect Nash equilibrium, we think player 1's subgame perfect Nash equilibrium payoff is in fact what's called a geometric series. Think back to your fond memories of plebe year calculus. There's a constant ratio between terms. Minus delta divided by 1 is minus delta. Delta squared divided by minus delta is minus delta. Minus delta cubed divided by delta squared is minus delta, and so on and so forth. And we see in this expression that each successive term in the series, we just multiply by minus delta again. And so the thing to remember then, what's the sum of a geometric series where the constant ratio has absolute value between minus 1 and 1, but not equal to minus 1, not equal to 1, strictly in between the two. And minus delta certainly satisfies that criterion because we stipulated that delta is strictly between 0 and 1. It's it's the first term, in this case 1, over 1 minus the constant ratio. So this is 1 over 1 plus delta. So we don't know yet that this is player 1's payoff in subgame perfect Nash equilibrium in the infinite horizon alternating offer bargaining game. But we do know that we feel pretty good about this being correct, and we're going to show that it's correct. Let's do the same thing for player 2. So player 2's payoff should be delta minus delta squared plus delta cubed minus delta 4th plus delta 5th minus delta 6th plus, and so on and so forth. And we can write this in a similar notation with the sigma. This is the sum as t goes from 0 to infinity of delta to the t we should write this as delta times minus delta to the t. Okay, so here we are. All right, so here's our sigma notation. We see again, here's the constant ratio, minus delta, has a power on it. Here though is our initial term, delta. Where do we see that over here? We see it here. Here's our initial term, delta. Instead of our initial term 1, there's really a 1 over here. Okay. And so what is this sum equal to? It's a geometric series. The sum is equal to the initial term, delta in this case, right here, over 1 minus the constant ratio. So this is delta over 1 plus delta. Note that if we sum these up, they sum up to 1. That tells us that we should think that when we find our subgame perfect Nash equilibrium, the path of play should be player 1 makes an offer and player 2 accepts. We'll find out what that offer is in a moment. And note over here that the payoffs in subgame perfect Nash equilibrium always added up to 1 as well. And we saw when we did 1 round and 2 rounds of bargaining that indeed player 1 makes an offer that player 2 finds acceptable, minimally acceptable, but acceptable nevertheless, and player 2 accepts. Okay, so we've used our finite horizon bargaining work to develop some intuition for what we think should happen in infinite horizon alternating offer bargaining. We took a limit of these payoffs. We looked at our pattern. We said we thought we knew what the pattern looked like. We took a limit. That's what we're doing here as we let the number of rounds go to infinity. And so we expect that player 1 in subgame perfect Nash equilibrium should get 1 over 1 plus delta. Player 2 should get delta over 1 plus delta. So now let's put up the tree for infinite horizon alternating offer bargaining. Let's derive the subgame perfect Nash equilibrium strategies. And then we'll see what the payoffs are in subgame perfect Nash equilibrium. Okay, so first let's put up our game tree. As before, this tree is going to have to be a sideways tree just because it's a big tree and we're going to need more space than we have vertically. So the game begins. Player 1 makes an offer. Remember, this is a share of the prize available, a share of the pie. Between 0 and 1. 0 means I'll keep nothing, player 2, and you can have all of it. 1 means I'll keep all of it, and you, player 2, can have none of it. And some number in between says I'll keep A1 for myself, and you, player 2, can have 1 minus A1. If player 2 accepts, the game ends. Player 1 gets A1. Player 2 gets 1 minus A1. Alternatively, player 2 could reject. Let's say P2, player 2. If player 2 rejects, now it's player 2's turn to make an offer. So player 2 chooses a number between 0 and 1, which represents an offer about how to divide the prize between player 1 and player 2. Player 1 now has a choice, accept or reject. If player 1 accepts, she gets A2 of the prize, but the prize is only worth delta now. Player 2 rejected back here, if we get this far, player 2 rejected, so the prize is discounted once. It's discounted by delta. Player 2 gets delta times 1 minus A2. On the other hand, if player 1 rejects, now it's player 1's turn to make an offer, and so on and so forth. What we're going to do here is write game repeats from beginning discounted again by delta. So since we will, when we get to this point where we say game repeats, player 2 rejected, player 1 rejected, To get to this point, we had no discounting. We discounted once. We discount again when the game repeats. So now player 1 makes an offer to divide a pie of size delta squared. Okay, and so on and so forth. So we're now ready to introduce a method to find the subgame perfect Nash equilibrium in this game. And the method is very similar. It's the same idea, although the technical implementation is a little bit different. It's the same idea that we saw in the dynamic arms race. We have a subgame that is strategically equivalent to the main game. So here's the full game. Player 1 starts. Here's the beginning of time. We go through 2 rejections. And we have a subgame that is a copy of the main game. And we can tell that because the way that we recorded our tree gives it away. It says game repeats from the beginning, discounted again. So it's strategically equivalent. They start dividing a prize, this time of size delta squared, rather than of 1. And then if there's a rejection, we discount to delta cubed. If there's another rejection, we discount to delta fourth, and so on and so forth. Okay. So we're now ready to find this subgame perfect Nash equilibrium. And we're going to use this game repeats from the beginning, discounted again, to make backwards induction work. The problem with backwards induction without some sort of little trick is that there's no last node to start from. So this copy of the game within the game will let us adapt backwards induction to this kind of setting. One thing to note, we actually aren't going to follow Rubinstein's method for finding subgame perfect Nash equilibrium. The story is that he wrote this incredibly important economic paper in a tent when he was serving in the Israeli army with a flashlight at night, because that was the only time he could write about economics. And so it's a great paper, but it's technically pretty complicated. So we're going to find, so a number of researchers have figured out other methods to derive this subgame perfect Nash equilibrium. And we're going to follow the method of, I hope I'm pronouncing this right, Shakad and Sutton. And we don't quite follow their method. There are a few little nuances that are technically important, but we will leave out. Okay. The important thing about this method is that we will be able to use backwards induction in a very similar way to the method that we used with 1 and 2 rounds, where we find what category of offers are accepted by a certain player at a certain stage, and then we allow the offerer to make a minimally acceptable offer to the person, to the player, making the acceptance or rejection decision. Okay. So here we go. All right, if you're following along on the notes at home, we're now at page 16, okay, where it says SPNE strategies and payoffs. Okay, and so we said we can't use backwards induction because the tree has no last node. So we need to do something to this tree, do something to this game, so that we can treat it as if it were a game of a tree of finite depth, a game of finite horizon, even though it's not. All right, so here we go. So here's how we're going to use this subgame identical to the main game trick. So first, we're going to suppose that Rubinstein's game has a subgame perfect Nash equilibrium. Note that there's no guarantee of this. There are infinitely many turns. There are infinitely many strategies available to each player. So there's no guarantee. We just say, suppose this happens. And either we'll work forward to find a subgame perfect Nash equilibrium. That's what will happen. There is one. Or another possibility that won't happen is that we'll work forward and we'll discover that this supposition was wrong. And then we'll be able to conclude, hey, no subgame perfect Nash equilibrium. Spoiler alert, we'll work forward, we'll derive a subgame perfect Nash equilibrium. Suppose there is one. Okay. If so, the subgame perfect Nash equilibrium strategies also, they also form a subgame perfect Nash equilibrium in this subgame. Why is this? This game repeats from the beginning. Appropriately discount is strategically equivalent to Rubinstein's game, which started up here. So if we have strategies that form a subgame perfect Nash equilibrium up here, since this is a repetition of the same game, just discounted by delta twice, here, discount. It must be that the strategies form a subgame perfect Nash equilibrium here. Okay, so fine. A subgame perfect Nash equilibrium has to have payoffs. So let X represent player one's subgame perfect Nash equilibrium payoff. So we don't know what X is yet. We're just letting it be a placeholder. It's just easier to write X, which is one little letter, than player one subgame perfect Nash equilibrium payoff as we go through this derivation. Every time you see X, though, you can substitute this phrase, because that's what X represents. So in essence, our goal is to solve for X, as they say. We want to figure out what X ought to be in terms of delta. That will tell us player one subgame perfect Nash equilibrium payoff, but it will also let us find these A1s and A2s and classify these acceptance and rejection decisions because if we know what player one's payoff is and A1 and X are expressed in terms of each other, we'll ultimately be able to solve for both A1, A2, and X, etc., etc. Okay. All right. So the last piece of this puzzle, the last part of using this game repeats from the beginning, discounted again trick. If player one's subgame perfect Nash equilibrium payoff up here is X, and we reject, and the game repeats from the beginning, discounted again by delta, we can replace this subgame, the game repeats subgame, by delta squared X. This is going to be player one's payoff in the game repeats subgame. We've discounted twice. X is the subgame perfect Nash equilibrium in the main game. So it must be that delta squared X is the subgame perfect Nash equilibrium in the subgame. If you want to, this will be correct, although you don't know that, we don't know that yet. You can also replace player two's payoff with delta squared 1 minus X. We don't actually know that yet. If we write it this way, we've assumed that the subgame perfect Nash equilibrium path of play has the form player one makes an offer and player two accepts, because these sum up to delta squared, or X plus 1 minus X sums up to 1. We really only need this piece of information, that player one receives delta squared X. Okay, so let's make that replacement. We're going to erase this. It's not that it's going away, it's still there, it's still a subgame. But part of backwards induction says as we work our way up the tree, what we can do, in effect, as we derive subgame perfect Nash equilibria, is replace the game tree of the subgame with subgame perfect Nash equilibrium payoffs. So player 1 gets delta squared x. Okay, so here was our trick. Subgame, strategically equivalent to the main game. And so here's our trick. Now we can treat this infinite horizon alternating offer bargaining game as a finite horizon game in which the last move consists of player 1 deciding to accept an offer and receive delta A2, whatever that may be, or reject and get delta squared x. So now we're down to 2 rounds in essence, although if there's a rejection instead of the game ending and both players getting nothing, player 2 is going to get delta squared x. And so now we're going to do normal backwards induction and work our way back up to the top of the tree. Okay, so this is still the shackhead second derivation. I'm going to take these steps off. Okay, so now what we do from here is going to look very much like the derivation we did on the Wednesday before spring break. For 2 rounds, for finite horizon bargaining, the only difference is that as we start off, player 1's acceptance rejection decision is going to be between delta A2 and not 0, but delta squared x. And this x is going to propagate its way up the game tree, and we're ultimately going to be able to solve for A1 and A2 and write down subgame perfect Nash equilibrium strategies. Okay, so let's. So now we're at the top of page 17, if you're following along at home. So what about player 1 down here? When does player 1 accept? Player 1 accepts whenever delta A2 is at least as good as rejecting. In other words, delta A2 is at least as good, greater than or equal to delta squared x. Okay. Player 2 then Player 2 makes a minimally acceptable offer. What does it mean to make a minimally acceptable offer? It means that player 2 looks at this inequality and says, I'll offer the A2 that makes player 1 indifferent between accepting and rejecting. We said on the Wednesday before spring break that if a player is indifferent between acceptance and rejection, the player will accept in subgame perfect Nash equilibrium. So player 2 is going to make a minimally acceptable offer. This is going to let us find A2 in terms of delta and x. We can divide by delta on both sides. Delta is not 0, so we haven't angered the math gods. This is a completely mathematically legal maneuver. Okay. So now we know if player 2 offers delta x, whatever that number may be, player 1 will accept. So now let's keep working our way up the tree. Player 2 accepts if we've done player 1's decision, we've done player 2's decision. Now player 2's acceptance versus rejection decision here is the one we're considering. If player 2 accepts, player 2 gets 1 minus A1. Okay. And she'll accept if that's greater than or equal to the payoff of rejecting. If player 2 rejects, player 2 offers A2 is equal to delta x. Player 1 will accept, and player 2's payoff will be delta times 1 minus A2. But we know that 1 minus a2 is equal to 1 minus delta x. So player 2 will accept if 1 minus a1 is greater than or equal to delta times 1 minus delta x. So now, just as over here we solved for a2 in terms of delta and x, we're going to ultimately solve for a1 in terms of delta and x. Player 1 makes a minimally acceptable offer, which is to say player 1 takes this inequality and chooses the a1 that makes it a true equality. Let's rearrange. 1 minus a1 is equal to delta minus delta squared x. a1 is equal to 1 minus delta plus delta squared x. Okay, player 1 offers us the top of the tree. So we've done the part of backwards induction that takes us to the top of the tree. However, we're still not quite done because although we've written down strategies, we've written down A1 and A2 and acceptance and rejection decisions in terms of delta and in terms of x. Remember that x was just a placeholder. X was our placeholder for player 1's payoff in subgame perfect Nash equilibrium. So we don't want to keep this placeholder around. What we want to do is solve for it in terms of delta, and then that will let us write down A1 and A2 in terms of delta. So we need one last little piece. Okay. What did backwards induction tell us about the path of play? Player 1 will make an offer. Here's the offer. And it's going to be acceptable to player 2. Player 2 accepts this offer. We don't know what x is yet, but it will be an acceptable offer to player 2. So that tells us, excuse me, that player 1's payoff in subgame perfect Nash equilibrium is in fact A1. Because whatever this is, we're about to find out, whatever this is, player 2 finds it acceptable. Okay. Sorry, 1 minus delta plus delta squared x. And player 2 accepts. Okay, so here's our path of play. X, though, remember that x we said was our placeholder for player 1's payoff in subgame perfect Nash equilibrium. So here we are. It's A1. Player 1 offers this, player 2 accepts. Here's player 1's payoff in subgame perfect Nash equilibrium. So A1 is equal to x. Okay, so now we have two equations, this one and this one, in two unknowns. It doesn't really matter which one we decide to solve for. Let's solve for x, which is equal to A1. So let's put x in here for A1. X is equal to 1 minus delta plus delta squared x. X minus delta squared x is equal to 1 minus delta. We're going to factor out x. x times 1 minus delta squared is 1 minus delta x. So now let's factor 1 minus delta squared. No quadratic formula required. Remember, the difference between two squares, this is 1 squared minus delta squared, is equal to the product of the difference times the product of the sum. And you can check using FOIL. First, outer, inner, last. 1 times 1 is 1. Here we are. Outer, 1 plus delta. 1 times plus delta is delta. Inner, minus delta times 1 is minus delta. So we have delta minus delta is 0. Last, minus delta times plus delta is minus delta squared, which we have up here. Okay. And so now what can we do? We can divide on both sides by 1 minus delta times 1 plus delta. This again, this is totally legal. Delta is between 0 and 1, but not equal to 1 ever. So the only thing we really need to be concerned about is whether this term, or this term I suppose, might be 0. But delta is not 1, which would make this term 0, and it's not minus 1, which would make this term 0. So this division is totally legal. And we can cancel 1 minus delta over 1 minus delta. So this is 1 over 1 plus delta. So you can rewind now. We said our intuition was that subgame perfect Nash equilibrium payoff to player 1 in the infinite horizon alternating offer bargaining game should be 1 over 1 plus delta. That's what our x is. Here it is. 1 over 1 plus delta. Okay. Since the path of play is that player 1 makes an offer, a1 is equal to x is equal to 1 over 1 plus delta. Player 2 accepts, it must be that player 2 gets 1 minus a1, 1 minus x, which is delta over 1 plus delta. So our intuition, while not formally correct, or not a formal derivation, did lead us down the right path. It led us down the correct path to finding the payoffs. Okay, so here are our payoffs. Last but not least, let's write down the subgame perfect Nash equilibrium strategies. Actually, before we do that, let's write them down over here. A1 is equal to 1 over 1 plus delta. Player 2 accepts. A2 is going to be equal to delta over 1 plus delta. Player 1 accepts. Okay. This is what they do. Let's write down the strategies. This is almost done, except accepting, accept EX, CE, PT, needs to be conditioned on an offer being good enough. Okay. So here's player 1's strategy. We need to write down what player 1 offers in round 1, round 3, round 5, and so on, in all the odd rounds, and what her acceptance criterion is in all of the even rounds. So we're at the bottom of 17. We're about to turn to the top of 18. Okay. So all of the odd offers are going to be 1 over 1 plus delta. Player 2 makes all of the even offers, and player 1's rule is accept an even offer if it's at least as good as delta over 1 plus delta. All right, now player 2's strategy. Player 2 makes all of the even offers. Every offer is a strategically equivalent decision to every other offer. Player 2 offers delta over 1 plus delta, and player 2's criterion for acceptance except if player 1 is keeping, no more than 1 over 1 plus delta. Okay, so here we are. We've written down payoffs, and we've written down strategies for subgame perfect Nash equilibrium. All right, so this is a slightly unusual format. There's a homework problem on problem set 5 that asks you to repeat this derivation, just as we did it in class. The goal of this problem is to give you practice writing it down and thinking it through yourself. This is, I think it's safe to say, one of the more complicated games we've seen so far. So you should practice doing it yourself. It usually takes several tries. I don't mind telling you that it took me probably 5 or 10 tries when I first saw this for it to really start to make sense. So if it doesn't make sense the first couple times, I mean, certainly get in touch with me. But please do try it yourself, and don't be discouraged if it takes a couple rounds, because that is usually what it takes. There's also an old final exam problem where Darth Vader and Lando Calrissian bargain. Darth Vader makes all of the offers, and Lando Calrissian makes all of the acceptance and rejection decisions. So a good way to test your understanding is to try to do that problem. All right, I hope you enjoyed this. I'll see you next time.